So, welcome to this talk. I'd like to talk about large graphs and graph databases. And I will explain what I mean by graph and what I mean by graph database and what they do and so on. But before we start, let me admit that I'm not Michael Hackstein. He was originally announced for this talk. He's a colleague of mine, but he fell sick yesterday, and so he really couldn't come. And since I'm here anyway, I jumped in. So my name is Max Neunhoeffer. I work for the same company as Michael, ArangoDB, and I'm one of the core developers and responsible for the distributed version of the database. So, I just grabbed his slides and I grabbed his talk, and so you have to live with me, but it's the same talk. Right. So let's start with graphs. When I talk about a graph in this talk, I mean something like this, with vertices, which are depicted by rectangles here, and edges, which are depicted by arrows here, and with some data which is at these vertices, and some data which is at the edges. So usually I mean schema-free data, so JSON objects typically. There can be a schema, but it's not necessary. And essentially these edges, these arrows, are a kind of relation between the vertices. Typically these edges have a direction. Sometimes one wants to ignore them, so you can ask for just ignoring the direction. And then what we talk about undirected graphs. Now, a graph database is good at storing these graphs and then querying them. So I will cover a bit what I mean by query them. The crucial thing is that querying a graph essentially means that one follows these edges in intricate ways. And the crucial thing is that before you start the query, you might not really know how far in the graph you have to go. So we follow edges, but essentially the number of steps we have to go for a certain query is not really known. That is what is typically true for graph database queries. Anyway, let's go in a bit more detail. Here's, for example, a graph which depicts friendship between people. So the vertices are people, and the data is just their name in this case. And the edges, there's an edge in both directions if two people are friends. So one typical query for that graph could be, give me the friends of Alice. That involves starting at a vertex and just going one step along an edge. Now, another query could be, give me the friends of Alice, but not the direct friends. So that would now involve to go in any possible way from Alice, from the vertex Alice, 2 steps, and find the places you can reach, but only take those which you cannot reach with a single step. Now, these 2 queries somehow contradicted my statement that I don't know beforehand how far to go, because in the first statement I said, well, go 1 step, in the second I said, go 2 steps. But sometimes we have questions like, give me a linking path from one vertex to another. And usually I'm interested in a short path. Obviously I can go a long way from Alice to Eve, say, or I can go in just 2 steps. And here you see 2 things. First of all, the length of such a shortest path is not a priori known when you ask the question. And secondly, even if you ask for the shortest one, it might not be unique. For example, this would have been a solution as well. Again, that's typical for graph queries. Another could be if you have a graph which depicts train stations and you have edges when there is a line going through from one station to the next. So for example, here would be the blue line or the yellow line. Now a question could be, if I have a ticket which allows me to go for 6 stations, that means I can go 6 steps in this graph, and a question would be, what are the stations which I can reach with this ticket? Now I have an upper limit, 6, but correct answers involve 1 step, or 2 steps, or 3 steps, up to 6 steps? And the answer can be a lot of different vertices. Again, a typical graph question. You see the pattern already? It is somehow linked data, and we follow the links with the questions. Another thing is pattern matching. Imagine, for example, a graph in which some vertices are people and other vertices are hobbies, and there's an edge from, say, Alice to hobby 1 if Alice practices this hobby. Now a sensible question could be, find, starting from Alice, somebody else who shares 2 different hobbies with her. So suddenly we have to look in this graph for a situation where we start with Alice, we have 2 outgoing arrows to some hobbies, to do 2 different hobbies, and then we have to go back and find another person who has arrows to the same 2 hobbies. And then, of course, we want to find all such configurations. So that is a general thing with pattern matching. There we look for patterns of paths or situations in such a graph. And again, sometimes we say it's exactly 2 steps. Sometimes we say between 1 to 5 steps or any number of steps. Everything is possible. Let me give you another example. If you run an online shop and you have customers on products and recommendations, you want to come up with a sensible recommendation for a user. So if we want to do that, we might do things like looking for patterns like Alice has bought something and a friend of her has bought the same product, and that friend has bought another product. Then you might want to recommend this other product to Alice. And again, you have a potentially large graph, and you look for patterns and structure in this graph to answer certain interesting questions. And again, it's all held together through these edges or relations, and that is what you are querying. Now, there could be further conditions, like here in this sentence I have count these friends, but look at product rating, give limits, or whatever. The sky is the limit. You can have arbitrary things. And so here you see it's important that both the vertices and the edges can carry data. And since we have sometimes inhomogeneous graphs with products and people, it's quite convenient if it's schema-less, because then you can put arbitrary structure of data in the various places. Now let me contrast this with a few queries which are not typical for a graph database. Imagine you have one of these graphs or whatever in your graph database. You might be interested in other things. For example, just look at the users and give me people whose age is between 21 and 35. Well, this has nothing to do whatsoever with the edges, with the relations. So that's not a typical graph question because it doesn't look at the edges. Or do some kind of aggregation according to the age of people. Again, a nice database question, but nothing to do with graphs. Or aggregate users by their name, look for people with the same last name, and so on. So even if you have graph data, there can be a lot of queries which are actually not really graph related. Now, let me spend a few minutes to explain how such a graph database can answer such graphy queries. So the typical thing we have seen, the pattern, is that you start somewhere in the graph and explore the vicinity of the graph by following the edges. And the formalization of that is something called graph traversal, and we just quickly run in this slide through how it works. Imagine we are looking for something close to this vertex S. So we pick a start vertex, and at first we just look, what are its neighbors? What are the outgoing edges? Say, these 3 are the outgoing edges going to 3 vertices. Now we might not be interested in all these edges. We might have a condition on the data which is on the edges. So we might apply some filters and just discard this one. But still we have 2 neighbors. And now, since we are looking for the vicinity and paths, we somehow repeat the same thing at the neighbors. So for example, we start with the first one and iterate, and we say, what are the outgoing edges from A? So now the answer is D and E, and again, we might filter out some, and then we're here. And now if we are, for example, looking for paths of length 2 with a certain pattern, then we would have found our first result here from S to A to E, and return this as one result. Now, if we are looking for all these paths of length 2, then we would backtrack, continue here for looking for more neighbors, but there are no. This is discarded. And so then we would have next to start here and go to an unfinished vertex and explore from there. And we find another path, we return that. Maybe there's no filtering out here. And we have now the result, which is two vertices, two paths of length 2. I think you get the idea. What very often is needed also for looking for short paths, that maybe you have to look from both sides or something like this, but essentially the idea is this graph traversal. And that brings me to the difference between graph databases and other databases. What you see here is happening in a graph database is this walking around in the graph and hopping around and finding paths and vicinities and exploring. That's not so much happening in classical databases or databases with other structures. And so that is somehow what makes it typical to be a graph database. Let's analyze this a bit and let's see how long things take and what kind of crucial operations are necessary for graph databases. So let's look at one of these steps. We are somewhere, we look for the neighbors. So what is the ingredient to do here? Obviously, when we have found the start vertex or the vertex where we are, which is usually a very quick lookup which can be done in constant time, then we have to find all connected edges. That is somehow the fundamental operation. We have to, if we are at a vertex, we have to find all the edges which go out, and together with them, the vertices where they go to. That is the fundamental operation, and depending on how you organize it, this is also a constant time lookup. On the other hand, if you count the length of a result, this can be large, so it's probably not completely right to talk about complexity constant here. But if you look through the outgoing edges and filter them out and apply some condition, then at the latest you have complexity n, where n is the number of edges going out of this vertex. Now obviously when you want to go this step to the other vertex, you have to look up this other vertex, which you usually can find in constant time, but for each outgoing edge. And then you have to filter on the vertices on the other side. So which essentially says this algorithm doing the graph traversal in one place has time cost approximately n, where n is the number of outgoing edges. So that's linear complexity. Now linear complexity doesn't sound very good, in particular if you think a very large graph, but let me contrast that if E is the total number of edges in the whole graph, that would be a disaster because this can be really, really, really many. But many graphs have only few relevant edges, that is, few edges which start actually here. And the graph traversal, in every place where it is, it only has to consider the outgoing edges from that place. And so far, therefore, it's not that bad. And in particular, we do some filtering, but for everything we find, we actually produce a result. And so therefore, it's not that bad because the work we have to do is somehow proportional to the amount of results we actually produce. In particular, this graph traversal doesn't get slower if the complete graph is large. It only gets slower if it has to find a lot of results. Now, that's the little caveat. If you have a highly connected graph where every vertex is connected to a lot of things, say in a Twitter follower graph or whatever, then if you increase the length of the paths, you get an exponential growth of results. Yeah? For example, if you take the typical friendship graph of humanity, you take the humans as the vertices and make an edge from between two humans which are friends, then everybody has potentially hundreds of friends, then it's a well-known fact that you basically have at most 7 steps between any 2 people on the planet. That is how highly connected this friendship graph is. And that indicates that if you would study this graph in a graph database, you would literally go to billions of results if you just say depth 7. So that's kind of what we have to keep in mind. Yes, we look for arbitrary path lengths, but depending on the structure of the graph, this can mean a lot of work and a lot of results if we increase these lengths. Now, I've always said graph database, and then I've said I work for ArangoDB. Well, ArangoDB is a graph database, but it's not only that. Because what we've found is that in many use cases, it is useful to have graph functionality and be able to query graphs. But it is even better if you can do other queries as well and store other types of graphs as well. So therefore, ArangoDB is a multi-model database. It supports multiple data models, namely key value pairs, documents in the form of JSON documents, and graphs. And actually, it's not separate engines, but it is one engine which has in one core all these data models. For example, we store a graph as a collection for the documents which represent the vertices, and a collection which represents the edges. And all the edges and all the documents are JSON documents, therefore we can store data with them. Now, the database has a single query language called AQL, which is similar in spirit to SQL, which allows to mix and perform document queries, graph queries, joins, all these typical things, not only graph queries, but also a mixture of graph queries and other queries. And all this can be done in the same statement. And if you run on a single server, then you have, even if multiple collections and multiple documents are occurring, then you have ACID guarantees. So that is this multi-model idea, and somehow my arguments about graph database extend to this multi-model stuff. But the topic of this talk is the challenges we face when we have actually large data and want to do graph queries. We've already seen what happens. We want to run around and hop around in these graphs and follow the edges and see what happens. Now, what challenges does this pose if we have big graph data? So let me just show an example, and then we study where this could run into problems. So that's an AQL statement, which is pretty easy to understand. It runs through all the users in the user collection and returns a JSON document for each. Now, obviously, I'm now interested in a graph query, so I have to say where I start. So I filter out the starting vertex by name, and this gives me essentially as a result just Alice. And you have to imagine that this user here is a JSON document. We naturally ask for the name component to be equal to the string Alice, and that is where we are. Now we can immediately start a graph traversal from here. So if I would say in a very similar way that I want to start outbound in the has bought edge collection at the place where a user is, that is in this case with Alice, and I just say don't say anything, then I go one step. So this query does one step towards a product. Here you can immediately see when this will be slow if Alice has bought 1 million items. Maybe she's a billionaire and buys a lot of stuff. So this becomes slow if there is one node which has a lot of outgoing edges. But let's go on. This is somehow the other example. We were looking for something Alice has bought, which has somebody else has bought the same, then with some conditions, and then something that other person has bought. That would translate in such a statement. Now I say I want to have 3 steps. I want to be able to I want to go backwards or forwards, depending on what is working. And I'm not only asking for the vertex at the end, but I'm also asking for the vertex, the latest edge, and the full path. And then I can formulate my filter conditions by using these variables which are just defined within this for statement. And I can limit according to attribute values, and I can limit to 10 and so on. So that's a typical query. Now you can see this runs into trouble if Alice has not only bought a lot of stuff, but this was bought by millions of users, and they have bought yet other products. So it becomes large if there's a lot of such paths. So essentially, we have seen two big challenges here. If it so happens that we run around in this graph and we stumble on a vertex, maybe as a starting vertex or as a vertex somewhere on the way, where there is a lot of incoming or outcoming edges. Say you do Twitter followers and you stumble on a celebrity which has millions of followers. Suddenly, the algorithms become slow. Just to look at all the edges which, say, come into Alice is really expensive because it's linear, as we discussed, in the number of edges adjacent with this vertex. But quite often, you don't need all these. If you need all the results, then you have to pay the price. But if in this graph, you only need a few of these many edges, because you have some other filtering condition, maybe something about the price, or I don't know. Then the big question is, how can you speed up such a query where you have a lot of edges in this place, but you are interested only in a very tiny fraction of them? And that is called vertex-centric indexes. The essential idea is that you have your graph, you have the outgoing or incoming edges from every vertex, but you want to home in on a certain selection of these outgoing edges, say, or incoming edges. So what you want is, we want, in database terms, you want to have something like a little index on the set of vertices going out of this vertex, on the set of edges going out of this vertex. So that's the vertex-centric index. It's a little index everywhere in the graph. And this can be achieved quite efficiently. For example, if you just take all the edges in this collection and you sort first by the vertex, the edges going in, say, and after that you sort by, say, timestamp. Then you can just do a range lookup by saying this vertex as incoming as two vertex, and then say the timestamp between here and there. And that is what databases are capable of. They can then home into the actual results very, very quickly. So the idea is quite simple. You want to have indexing facilities which can first say where we are in the graph and then fulfill other conditions. That's called vertex-centric indexes. So that was a neat little idea, but it has nothing to do with really big and scalability and so on. Now let's really go big. What happens if you have a graph which does no longer fit on a single machine? Literally the Facebook graph or the Twitter graph or whatever. If it doesn't fit on a single machine, what can you do? Well, these days the answer to big data is scale out. Obviously you can buy a bigger machine, but this has some limits. What you want to do is you want to have a database, a graph database, which scales out to multiple commodity hardware machines, and you want to shard your graph. You want to store parts of it here, parts of it here, parts of it here, and all together you have the complete graph distributed across your cluster, and then you want to do graph queries. Now, what are the challenges here? You have to say how you query. You see, a graph database isn't done with just storing your data. You want to be able to query it. And now if you hop around in your graph and that is distributed all across the network, then you are going to have a lot of communication in your network, and that will become slow. Imagine a random access to memory is at least 10,000 times faster than a network hop to another machine, just to ask what is the neighbor. And if we don't want to lose this factor of 10,000 or 100,000, we have to be really careful. So therefore, you have to reduce network hops. Vertex-centric indexes, the idea I mentioned just now, do help a bit, but essentially just on a single machine. Yeah, because usually it's very difficult to have a global index across sharded data. Therefore, what can you do? If you do it naively, then you have a nice graph, and imagine this has billions of edges. You distribute it in a nice random way, which makes sure that equal parts of the graph are distributed across my machines. You end up with this. The vertices, the edges are randomly distributed. This trick always works. It leads to a nice uniform distribution if you choose your hash function correctly. But imagine you have to do a graph traversal here. You find your starting vertex here. Now you have to ask everybody what are the outgoing edges from this thing. A lot of network communication, nothing will really work. A lot of network overhead, very slow results. Now, what is the answer to that? Well, what we observed is that in many, many real-world applications, you know something about the graph, and the graph has a certain structure. Imagine you have a graph where the vertices are customers, then they live in some country. And if you're lucky, then most connections between customers will be in the same country. So what you can do is, you can say, I use the domain-specific knowledge about my graph, let's say the country attribute, to distribute the vertices of my graph by country. That is, usually two vertices, two users in the same country will be on the same machine. Then it looks more like this. Some highly connected part of my graph is on one machine, another part is over here, and the third is here. And yes, there might be edges which go from machine to machine, but they are rare. So therefore, what we have implemented in the enterprise edition of ArangoDB for the scalable graph cluster is that you can use domain-specific knowledge to inform the sharding to make it work better. And what happens then is, if you don't look for this, and you are looking for some path, say here, the red one, then this graph traversal will go all over the place, back and forth, very slow, very much network traffic. But if you distribute your graph a little bit more intelligently and use the structure of the graph and data locality, then okay, you still have to cross network boundaries sometimes, but for example, this graph now can be explored on this side here to some extent. Then there's a network hop to go to another place, and then the rest can be done here, which leads to the fact that for the same graph traversal, the same data, you suddenly have a lot fewer network hops and a very high speed up. Let me conclude, I think I have only 1 minute left, by talking quickly about index-free adjacency. Many graph databases advertise that they use index-free adjacency, which means that they keep the edge data close to the vertices they are connected with. Essentially, they put a flat array of edges next to each vertex. Now, that has some advantages. People claim that it's very, very quickly to find the neighbors. But imagine you combine this with a sharding approach. Then you somehow have to decide where you keep the data. Yeah? Because typically an edge can be connected to two vertices, and they might reside on different machines. Well, do you then store them doubly? How do you maintain all this? And that's actually a big problem. What we claim is that using an index to find the adjacency is much better in many ways, because you can now use index-free adjacency, as I explained in the first challenge, and you can double the edges in both locations, but you can now use index lookups to quickly find your edges and can maintain your data in a much more efficient way. And with this, I thank you. This is Michael's contact details, but you can find me as well. And I'm happy to answer a few questions. We might have a few minutes. Thanks. No questions? Yes?
The domain thing that you have said, I have two questions.
Yes? There's a microphone. Otherwise, I would have to repeat the question. While the microphone is reaching you, I have put a few ArangoDB t-shirts here, and everybody is welcome to grab one after the talk.
Hello?
Yeah.
First question is, with the domain thing that you have said, do I have to look for the domain, or the database does automatically?
Good question. In our approach, it works in many cases much better if you as the user can tell the database what is the crucial attribute. So therefore, you have to specify what attributes on the vertices to use to do the distribution. And from then on, everything is automatic.
Do you heard me? Yeah. And the second is if I can use double indexes or only one.
In ArangoDB, you can have as many indexes as you want. And a graph traversal will use essentially any index which sorts first by either from or to. And if you add further attributes to sort, then you get essentially an index, a vertex-centric index. But you can have arbitrary other indexes, geo-index, sorted index, hash index, and can therefore also do queries which are not graph queries at all. Yep, there's another question up there.
Super good talk, thank you. I was wondering how you maintain safety if you don't have ACID guarantees between your shards.
That's a very good question. The published version of ArangoDB does indeed not have ACID in the cluster, because that's a very difficult problem. We have plans to get there, but so far the atomicity is on the document level. Yeah? And obviously, if you remove Vertex using the graph API, then it will at the same time remove all the edges which are adjacent with it. That is done, but we don't have as isolation. So therefore, if you have a transaction which runs concurrently and which goes through this vertex, it might see part of the edges. That is a problem we are going to fix, but that's a very hard problem, and therefore currently we don't maintain consistency there. In a single server, all this is done transactionally, and you have the guarantee, the ACID guarantees. Okay, I don't see more. Yes, one more question.
Hi. Does Arango has any feature for taking some metrics about the graph, or just for querying?
Yeah, we have some, but many such metrics don't really scale. Not because our implementation is bad, because the algorithm is bad. So for example, you have a lot of algorithms which have complexity n to the 3, where n is the number of vertices. We do offer them, but they will only work in very small cases. And we have shortest path. We have shortest path with weights, but it's quite limited. What we also have is an implementation of the Pregel framework, and there you can run algorithms like PageRank in a parallel fashion. And so this kind of things which can be done in this Google Pregel framework can be done as well. But things like give me all the distances between any 2 points, they are just expensive and will not work in a large graph.
Thank you.
Okay, thank you very much. I'm happy to answer more questions, but I think we should stop to free the room. And please help yourself with t-shirts and stickers. There's a code, the color says the size. Thanks.